Today, we are going to be talking about a really important concept that's covered and used kind of to explain a lot of different things in chemistry, and it's called effective nuclear charge. And effective nuclear charge is essentially, we'll get into it, an interaction between the protons and the neutrons within an element, and it can run the effect of changing how big an atom is, how strongly an element holds on to its electrons, and a whole bunch of other things. And so we're going to kind of start with it today, and then we're going to talk about some periodic trends that are associated with it starting tomorrow. So the first thing that you need to understand is that inside an element, there are kind of always two forces at play, and it really depends on the type of particle that you're talking about. So if you go back to kind of your basic days in physical science, you can think of two different kinds of charged particles, a positive proton and a negative electron. And if you think about your IPS days, if I take something that's positive and something that's negative and I put those two things together, they are going to attract to each other. If I take two things that are positive and put them together, they are going to repel. And if I take two things that are negative and I put them together, they are going to repel as well. So when we talk about charges and things going on inside of an atom, there are usually kind of two forces that are going on. What ends up happening is that if you are an electron hanging out in the outside part of your atom in that electron cloud, you are feeling an attractive force or a pull from the nucleus on you as an electron, because a nucleus is positive and an electron is negative. So those two things are magnetically attracted to each other. However, around your element, you have other electrons in pretty much everything except for hydrogen. And so those electrons that are around your element are negative, as well as you, the little electron we're talking about. And so what happens is when those electrons interact with each other, they push each other away. And so your element, as it sits in its normal state, exists as a equilibrium or balance between the strength of the protons pulling in and the push away from those electrons that it's hanging out with. And the size that it sits in, the energy kind of its state, that is all affected by that relationship. So kind of like I said, you have your positively charged nucleus. Some of the electrons cancel out the attractive force, and if there's any electrons further out past the electron you're talking about, they don't really do anything. But we are mostly going to be concerned about electrons on the outside. So what happens is if we talk about the behavior of an atom, most of the time it's affected by the element's electrons in the outsidemost shell, which is called the valence shell. So the valence shell and how that element's electrons react is related to something called the element's effective nuclear charge. So the effective nuclear charge is a mathematical calculation that represents the balance between the pull and the push. And the way that you calculate the effective nuclear charge, which is called ZEFF or Z effective. Z represents charge most of the time. So ZEFF is the charge there, is actually calculated by taking Z for the element minus S. And you say to yourself, what does that mean? So Z is your element's atomic number, and S is your number of core electrons, not the valence electrons. You're like, what does that mean? I'm going to show you an example. Okay, let me get my doc cam up here. So we're going to do a Z effective calculation, or an effective nuclear charge calculation for the element phosphorus, P. So if you find the element phosphorus, it has an atomic number of 15. And I always find that it is helpful when we are thinking about effective nuclear charge to start off with by writing a shorthand electron configuration. So it has 15 electrons for phosphorus. Phosphorus's shorthand electron configuration is going to be neon in brackets, and then 3s2 3p3. Hopefully you understand that. If you find yourself still struggling with electron configuration, make sure that you contact me so we can get things cleared up. So when we talk about our shorthand configuration, the nice thing about our shorthand configuration is that it actually breaks our electrons into core and valence electrons without us realizing it. The elements' core electrons are represented by the elements that you put in brackets here. So neon has 10 electrons because it's atomic number 10, which means that neon represents 10 electrons in our electron configuration. These 10 electrons are our core electrons. And what I mean by core electrons is if we talk about our shells, these guys are the electrons that are not in the outermost shell. So if you think about, this is a very crude drawing here, but phosphorus has 15 protons. And if you think about how the shells are kind of set up, our first shell is the 1s shell, and it contains 2 electrons. The second shell, the 2s, has 2 electrons, and then the 2p has 6 electrons in it. The final shells on the outside are our 3s shell, which has 2 electrons, and then our 3p shell, which has 3 electrons. And you might say to yourself, hey, why is the valence not just this final shell here? When we talk about the valence, it's actually kind of the final grouping of numbers here. So this 3s and 3p are considered part of the valence. So when you look at a shorthand configuration, 10 electrons, basically the stuff in your brackets, that is going to be your core electrons. And then these guys that aren't part of that are going to be your valence electrons. Okay, so if I want to figure out my effective nuclear charge, and I write my Z's with a line through them because my 2's look too similar, what I'm going to do is I'm going to take the atomic number of phosphorus, which is 15, and I'm going to subtract from it the core electrons, okay? So the core electrons are going to be 10. I'm going to get, for my Z effective or my effective nuclear charge, I'm going to get 5. When we talk about effective nuclear charge, the larger the number is, the greater the effective nuclear charge. So if something has an effective nuclear charge of 1, that is going to be less of an effective nuclear charge than 5. Okay? So when you see this number here, the bigger the number, the higher the effective nuclear charge. And what that means for us is that if something has a greater effective nuclear charge, it means that it has a stronger pull on the nucleus than something that has a smaller effective nuclear charge. So if I see something that has an effective nuclear charge of 2, it means that that element's nucleus is not pulling on it as strongly as something with an effective nuclear charge of 6. And we'll get into that in just a second. Okay? Now, this is where we kind of wade into this issue here. This is a photoelectron spectroscopy picture, or a spectra, of lithium and beryllium overlapped with each other. So beryllium is represented in pink and lithium is represented in blue. So here is my question for you. Of lithium and beryllium, from which element is it easier to remove a valence electron? Why? And explain. So if you think about these, the blue set and the pink set, the first thing you have to ask is, which element is it easier to remove a valence electron? So if you think about when we talked about your PES diagrams, we always find the highest energy peak first and work our way out. So in this case, the highest energy peaks are located kind of around this 10 energy mark, and then we go down from there. So these 2 electrons here represent the 1s electrons for our elements. The pink is the 1s electrons for beryllium, and the blue are the 1s electrons for lithium. When we go here, beryllium has 2 electrons because its electron configuration is 2s2. Lithium's is 2s1. So if we look here, it requires less energy to remove an electron from lithium than it does to remove the electrons from beryllium. These peaks here, this tall one and this slightly shorter one, represent the outermost peaks for our elements, beryllium and lithium. But if you look at it, it's more energy to take those electrons away from beryllium than it is for lithium. Okay, and that is something that when we get into periodic trends, we are going to predict a lot of, but what we need to do is explain that. And when we are talking about elements that are side by side in the same period, so if we're talking about two things that are neighbors or things that are in the same horizontal row, we always talk about something called effective nuclear charge to explain that. So I'm going to go back to my notebook here and my doc cam, and hopefully we'll get that cleared up. Okay, so if we find lithium and beryllium here on the periodic table, lithium has 3 electrons and beryllium has 4. So what I want to do is I want to calculate our effective nuclear charge first. So we're going to do lithium first. Lithium's electron configuration is helium in brackets and then 2s1. If we think about its element setup, we have 3 protons in our nucleus. The 1s shell contains 2 electrons, and then the 2s shell contains 1 electron. Okay? If we think about beryllium, beryllium's electron configuration is helium, and then it's 2s2. So it's not that different because they're just neighbors on the periodic table. They're only different by 1 electron. So beryllium has 4 protons in its nucleus, and then its 1s shell also has 2 electrons, and its 2s shell has 2 electrons in it as well. Okay, so when we calculate our effective nuclear charge for both of these, what we're going to do is we're going to take its atomic number, in the case of lithium that's 3, and we're going to subtract only the number of core electrons. So that's the number of electrons in that noble gas, which is going to be 2. So our effective nuclear charge for lithium is 1. Our effective nuclear charge for beryllium is calculated with 4 protons minus its core electrons. And that gives it an effective nuclear charge of 2. Now you might say to me, Mrs. Ottemeyer, there's more electrons, so why don't I subtract the electrons, just those core ones come off? Why is that? So when you think about it, the core electrons are the ones that kind of provide what we call a shielding effect. We're going to talk more about shielding in just a little bit, but they provide what's called a shielding effect. And so these here block some of the influence from the nucleus. So if I have electrons if we're talking about these electrons out here, this electron is being pulled toward the nucleus. But these electrons in the core here, these 2 electrons in our 1s shell, are preventing them from being pulled in too far. They are pushing back on those electrons. The same thing is happening in beryllium. So these electrons in the valence shell, even though there's 2 of them, are still only being pushed back by 2 electrons. But what's different about beryllium is instead of having 3 protons like lithium, beryllium is going to have 4 protons pulling in. So if you think about magnets, there are 4 positive things pulling these electrons in, and there's only 2 electrons kind of pushing back. If we talk about lithium, there's only 3 pulling and 2 pushing. So what happens is the electrons in beryllium are able to be pulled in stronger because of the greater effective nuclear charge. So the moral of the story is if there is a larger effective nuclear charge, that means your nucleus is holding on stronger. I'm going to stop for a second so I don't spell it wrong. And if your nucleus is holding on stronger, it's harder to remove things. So if I go back to my spectra, kind of a lot of clicking back and forth here, I apologize. If I go back to my spectra here, and I take a look at what's going on, my lithium has a lower energy required to take off that one electron. And that's because the nucleus isn't pulling as strongly as the nucleus in beryllium. And so beryllium has a higher energy for each of its energy values to take off its electrons because it has a stronger pull from the nucleus, or a higher effective nuclear charge. Now, the thing about effective nuclear charge is it only works when you are talking about things that are in the same period. So I would not want to use effective nuclear charge as a comparison if I'm talking about lithium and sodium. We'll talk about that in the next video. But when we're talking about effective nuclear charge, it's an argument that works beautifully for things that are next to each other or in the same period. Because what happens is as you go deeper and deeper into the period, you get a greater effective nuclear charge. And always, if there is a greater effective nuclear charge, it means that that nucleus is pulling on those electrons for that atom stronger. Okay? Your homework that you're going to be doing is going to be asking you some questions about effective nuclear charge and explaining that. So hopefully this clears things up a little bit. We will be touching back on this when we talk about things like ionic radius or atomic radius, or even ionization energy with periodic trends, but this is kind of the general intro for it. In the next video, I'm going to talk to you about electronic shielding a little bit so we can talk about things that are in the same chemical family. If you find yourself having questions, please get in contact and we'll get things cleared up. Thanks.